and now is continuing in collaboration with Stellar Variability Group in IAA SESIC and the preparation team for Mission Plato 2. Let's me to have a brief biography. I'm from Iran, a country almost far from Spain, and less or more near to the latitude of Spain, and also very similar in culture and also climate. This is Iran's map. Different cities of Iran are shown by their almost historical famous sites, and it's Tehran, the capital of Iran, and this is Kerman, my home city. I'm from Kerman, and almost far from Tehran, with around 1,000 kilometers this distance. And I got my PhD in Azerbaijan, of a part of Iran, and also I graduated from my MSc in this part of Iran, and now I'm here. Okay, let's start by taking a look to history of variable stars. This is a list of first discovered cases of variable stars. The first variable star was discovered by David Fabricius. That was a long period mirror variable star. He saw it in August 1596. And then the star disappeared, and again he was surprised to see again the star in 1906. And this is this star when is in its maximum brightness, and this is when the star is in its minimum brightness. And pictures are taken from different places, and also different dates. The maximum maximum brightness on July 2004, and the minimum brightness on October 2005. This is the light curve of a mirror type star. Let me to have a brief definition about light curve. Light curve is simply a plot of the appearance magnitude of a variable star versus time. It means here in x-axis we have the time. Time goes in this direction, and here in y-axis we have magnitude or brightness, or maybe flux, and the brightness of star is changing with time. This is light curve of our variable stars. And mirror types, we expect mirror variables to be very cool red giants. They have long periods and large amplitude of light variations, and because of this, we can see them. I mean, the first person discovered a mirror type variable star, because in this year he didn't have telescope. So this is a kind of variable tree for astronomical objects. In the intrinsic branch, the pulsation stars are kind of variable stars, and this area is where we are interested to study. And This type of stars are target to be studied. And in astroseismology, we are interested to the pulsating stars because studying of the pulsations can probe the interior physics of star. And it's our goal in astroseismology. Okay. What are pulsations in stars? The simplest mode in a pulsating star is a simple expansion and contraction. As you can see here for star with expansion with the variation in radius, the brightness is changing. This is the fundamental radial mode for a three-dimensional sphere as a star. And the spherical quantum numbers are in this range, in these values. And the same, this is the fundamental mode for a two-dimensional environment as the head of a drum. And this is what we see as the fundamental mode for a one-dimensional environments such as pipe. And also for a three-dimensional environment like a spherical star, we have non-radial modes. When the L and M is changing. For example, here we have we will have a non-radial mode when the L is equals 1 and here M equals 0. It means in the azimuthal direction we don't have any node. And when M equals 1 means in azimuthal direction we have a node, and we expect for a three-dimensional environment that the node would be a line, a surface. And here when the L equals 2, we have two nodes, and two nodes when one of them is in azimuthal direction. And simply when we have these quantum numbers, we can see this kind of movement in the surface of the star. And when L equals 2, we can see this movement for the surface of star. And this is the pulsation in stars. Okay. You can see here the distribution of pulsating stars, different types of pulsating stars in the HR diagram. This double line shows the zero-age main sequence, and these two parallel gray lines limit the instability strip where the classical pulsating stars are located. And here in the lower part of instability strip, in the main sequence and also just above the main sequence, There is a group of pulsating stars, Delta Scuti stars, that are interested for us to be studied. And also you can see the evolutionary tracks with different mass of stars, or different mass of stars, and these stars have different temperature range, different brightness, different masses, different radius, and in an astronomical aspect, we have different driving mechanisms. Driving mechanisms means the way that energy is fed into the pulsation of star, and it could be fed into the star as a heat engine, for example, like a Kappa mechanism that is based on the opacity in star layers, and could be in stochastical driving mechanisms, for example, in solar-like stars, and we have Kappa mechanism in Cepheid, variables, or Lyrae, Delta Scutis, and this is another difference between the types of pulsating stars. So for Delta Scuti stars, the first detection of the variability was discovered by Campbell and Wright in 1900, and they just reported some variability. And in 1935, these people determined the period of variation in the Delta Scuti star itself. And finally, again, in 1956, established a new and separate group for pulsating stars as Delta Scuti stars, and also Brickman and Breger have done some calculations for this kind of stars. And also I know Rodriguez has done a catalog on Delta Scuti stars in 2000. And the effective temperature of these stars in this range, and they have a spectral type between A to F. They have intermediate masses. It means they are in the transition region between low mass stars that have convective envelopes and the high mass stars that have radiative envelopes, and they have short periods, less than 1 day, and they show pressure modes, and sometimes at the same time gravity modes. Both are excited by mechanisms in the star, and the Delta Scuti stars are excited by, are divided by, divided to two groups, HADS and LADS. High amplitude Delta Scuti stars, which typically show amplitudes bigger than 0.3 magnitude, and LADs, which show amplitudes smaller than 0.1 magnitude. And here, for our study, we considered the light curve observed by TESS transiting exoplanet survey satellite, the telescope by NASA, that is being the exoplanets by transiting way. And you can see here a light curve of Delta Scuti star. I want to introduce you the Fourier transform, a linear equation can take the light curve from the time domain to the frequency domain. It means when we have a light curve as a collection of different sine functions, but using the Fourier transform, it can be to the frequency domain. It means the different sine functions can be separated and can be arranged by their frequencies, but the frequencies they have. So this is the power spectrum or frequency spectrum of a pulsating star. And the question is why we need complex network approach for studying of pulsating stars. The reason could be because the linear models cannot entirely describe the stellar pulsation stars features or simply the light curves. Here you can see a light curve of Delta Scuti star. In astroseismology, people usually use this linear model to describe the light curve, but we know in some pulsating stars there are some features that cannot easily described by this linear equation. For example, this is a bump in R light curve, and it could not be modeled by the Fourier transform, because you can see here the distance between the model, the red dashed line, and the real light curve, the blue line. And it's the reason we are thinking about a way to be able to model star, the whole star with all of the mechanisms that make this non-linearity in stars. So some studies show interactions between modes and convection zone can be the origin of some linearities in Delta Scuti light curves, and complex network is a very young interdisciplinary field of study. If you look at this figure, this shows the citation rate against the time, and for these two papers, the citation has accelerated from after the 2000s. These two papers discovered complex networks. The first one applied random graphs, and the second one applied the network science in social science. And because of this, we call the network science at the science of 21st century. And in complex network, we combine ideas from mathematics, physics, biology, computer science, social science, and it has been used widely in many areas of science. And this list continues because I just considered some of the some important citations in different fields of studies. And so now we have complex networks that are applied to describe complex systems. But what are complex systems? Complex systems have a set of elements that can interact with each other and consequently, the complex system show emergent collective properties. It means you have some emergent collective properties, and you cannot distinguish these properties are due to which part of the system, because the elements are interact together, and all of them are responsible. All of them together are responsible for the emergent collective properties. The graph theory is the mathematical model we use for modeling complex systems. Graphs contain nodes, you can see here, nodes, and nodes or vertexes, and edges or links that connect nodes. And a graph is used to model a complex system when the elements are mapped into nodes, and the relation between elements are mapped as edges or links between nodes. So the graphical representation and complex network are the same. People usually use both of them for a graph or a network. So we have different types of graphs. Here you see an undirected network. In this network, nodes are simply connected, but in a directed network, the connections have directions. It means, for example, for the first node is connected to the second node, but the second node is not connected to the first node. And also we have weighted graphs. It means some interactions between elements are stronger than the other interactions. For example, imagine node 2 and node 4, and they have stronger relation rather than the 4 and 0. And we construct complex network or graphs for pulsating the stars by using the visibility algorithm. We have two kinds of visibility algorithms. The first one is a natural visibility algorithm that may make the natural visibility graphs, or NVG, and the second one is horizontal visibility algorithm that make the horizontal visibility graph, or HVGs. And in this algorithm, we use the real light curves observed by TESS. For example, this is a light curve. And if we magnify on the points of light curve here, the points, different point of the light curve can see each other by straight lines of sight. The red lines, I mean. And if each point is mapped to a node in the equivalent graph, if 2 points can see each other by a straight line of sight, the points are connected but links or edges in the equivalent graph. For example, the first point here can see the second point, but cannot see the third point. And here, the first point is connected to the second, the first node, sorry, is connected, because this is the equivalent graph of the type series or a light curve. is connected to the second node, but is not connected to the third. And in this situation, the point satisfies this mathematical relation. And for horizontal visibility graph, the story is the same. Nodes in the equivalent graph can be connected to each other if the equivalent points can see each other, but only by a straight horizontal line of sight. It means, for example, this point only can see the next points, but cannot see the points that have heights less than the next points. I mean, the points should satisfy this mathematical relation. Point A and B can see each other by a straight horizontal line of sight if they have higher than point C with YC height. And by applying the algorithm, the natural visibility algorithm, we obtained these graphs for different types of star. This is for a solar-like star, and this is for a Gamma star, and this is for a S is fine, it's a kind of Delta Scuti star, and this is for a Delta Scuti star. And you can see they show different graphs, and it could be motivate us to consider this approach as a way to classify the pulsating star. And for this goal, we should we should study the network parameters as the topological parameters. We have local metrics and global metrics. Local metrics such as degree of nodes, clustering coefficient, and page rank. And it continues because we have many local metrics, but I just consider some of them that I studied here. And global metrics like average velocity, transitivity, average shortest path length. Let me explain briefly about them. The degree of node means the number of edge for each node. For example, in this graph, this is small graph, the degree of the first node is 1, and the degree of node for the second node is 3, because 3 edges are connected to the second node, And this is the probability distribution of degree of nodes. You can see the degree of 2 has the biggest probability, because most of points in the equivalent graph have degree 2. This node has degree 2, this node has degree 2. So most of points of the graph has degree 2, and this is the probability distribution. We will speak about this distribution in next slides. Clustering coefficient defines as the tendency of connection between the nodes' neighbors. Consider this node. These yellow nodes are neighbors, and clustering coefficient could be 0 if there is no connection between neighbors and could be one if all neighbors are completely connected together. There is no other space for connection. I mean, all connection are filled, are completed. And we have also PageRank. PageRank measures the importance of node, what the Google or search engines use. And also for average clustering, we simply take an average on the clustering coefficient for different nodes. Each node has a clustering coefficient, and for having an average, just we take an average on clustering coefficients, and transitivity is less or more near to the average clustering concept. It means the number of triangles in the graph on the number of triples that need another edge to be a triangle. For example, here we have two complete triangles, and we have some triples that they need another edge to be a complete triangle. So, and the average shortest path length. Path length is the number of eggs between two nodes. Consider first node and the fifth node. The path length between these two node in this way, in this path is 2, and in this path is 4. And when we see the shortest path length, we consider the shorter one, 2. The shortest path length between the node 1 and the node 5 is 2. And when we take an average, we take an average for all nodes. And usually you need to tell the code the origin node or the destination node, because you want to know the average shortest path length for the first node or for the second node. It's a little bit complicated. And here we considered horizontal visibility graphs for our sample that contains around 70 Delta Scuti stars, includes HATS, high amplitude Delta Scuti stars, and LAGS, low amplitude Delta Scuti stars. And we just plotted the transitivity versus the average clustering coefficient, and you can see HATS and LAGS are clustered in two overlapping groups. The triangles show HATS, and the circles show LAGS. HATS show lower average clustering coefficients and higher transitivity values. And also they have lower surface gravity values, as we expect for evolved stars. And here we consider the size dependency of the average shortest path length for stars, and also the deviation for a random network, because the linear dependency of the average shortest path length to the size of network can tell us about the small worldness of the network. And we can see here the triangle shows triangles are for one HATS star, and circles are for a LAGS star. And we considered different size of network, and we measured the average shortest path length for each size. and the same for each size of a network for a lat star, and we see a linear dependency for both of them, and both of them are deviated from from a random network. This idea is from this study, and also both of them deviate from a random network that shows they do not originate from random mechanisms. And here, we considered this equation from this study. This is the probability distribution of nodes, as I explained during some previous slides. And for an HVG network, for any random time series with arbitrary generating probability distribution. It means you can use any random time series, make the network, measuring the degree distributions, and plot the probability distributions for degree of nodes. And we expect to have this distribution following this equation for any random time series. So we think about applying this approach for noises in our stellar light curves. And just for testing that, we considered a white noise as a random time series with Gaussian probability distribution, and this is the degree distribution of a time series which was generated by a Gaussian probability. And you can see this distribution is excellently matched with the theoretical equation. And also we measured the distance between these two distributions by the Kolmogorov-Smirnov distance, and it is around 0.004. And if noises in stars follow this algorithm, we expect such distances for them. So here we considered a real star. This is the light curve of this star. This is light curve of this star observed by TESS. The power spectrum showing many frequencies in the frequency spectrum of star, and in this process we generated the networks, we measured the degree of nodes, and we plotting the probability distribution of degree of nodes. And you can see here, this is the theoretical equation I showed you in last slide, and this is what we see from the original light curve, degree of nodes of the original light curves. When the light curve is mapped to a graph or to a network. So then we applied a pre-lightening process, and we just removed the highest peak or the dominant frequency. You can see the residual as a red light curve, and you can see the highest peak is removed in the frequency spectrum. And again, the network is making, the degree of nodes is measuring, and the distribution of degree of nodes is nearer to the theoretical line. And here, the green light curve shows the only background noise, because we removed all frequencies of star, and here there is only the background noise. We expect to have a background noise, and now we can see here that the distribution, the degree distribution is good matched, is excellently matched, and it in the range we expect for that. Okay, this approach is continuing. I need to test it for different types for different star, Delta Scuti stars, and also different types of pulsating stars to be examined, and it is my current work and my future work. And finally, we are considering the Kullback-Leibler divergence, or KLD analysis for our light curves. In this method, we should consider the directed horizontal visibility graphs to measure this method measures the reversibility in the networks, the light curves, and it could be checked by considering the distances between two distributions. Here we have a distribution for ingoing degrees and a distribution for outgoing degrees. What does it mean? Here we have a directed graph for each node. You can have a degree distribution for ingoing edge. For example, for first node, we have one ingoing edge and two ingoing edges, and for the second node we have one outgoing edge and two ingoing edges. Okay. For each degree, we have ingoing degrees and outgoing degrees. Then we can plot the probability distribution, as I explained you in the definition of degree of nodes. You can plot the probability distribution of ingoing degrees and outgoing degrees, and Kullback-Leibler divergence is defined as this relation between P in and P out. And okay, we are starting to apply this approach for the real stellar time series. This is a real time series, and a directed horizontal visibility graph is built when we just go in direction of time, and each node will have will have such in degrees and out degrees, and then we can have two distributions for in degrees and out degrees. This is degree of nodes. The red lines, solid line or dashed line, are for in degree distribution, probability distribution, and the black one are for out degree probability distribution. And just to be considered with gap, light curves includes gap, and light curves not included gap. And there are some differences. We are working on that, and we can see differences between the in degrees and out degrees distribution. And finally, we have this result for the measured KLD values for HADS and LADS, this figure is very rare. We are studying this, we are considering different ideas about this, and just I wanted to show you for a way we are thinking about to help us to know about the dynamical process behind the pulsations. And the idea was from this paper. He tried to explain the process, the dynamical process by the KLD values, and we're using that, applying that for our stellar samples. And for this study, TESS light curves were applied, and also we used Gaia data, and this study was funded by Iran National Science Foundation in my previous postdoc when I was in Iran, and also is continuing by this foundation and several other grants in the IAA. And thank you for your attending.
Okay, thank you very much. And the talk is open for questions. Also, for people in Zoom, if you want to ask some questions, please raise your hand. Here.
Yes.
You first.
How do you when applying Delta Scuti that we are again when you use your argument, the results with from the output are somehow for analyzing the stuff. I mean, do the algorithm is useful for what?
Okay, yeah.
I don't know the stuff.
Okay, there are lots of ideas for us to continue. The first idea I applied the network, a complex network approach, was something like classifying pulsating stars. And it is still it is still in progress, but it's difficult. And now I'm thinking about in Delta Scuti subclass, we have a variety of stars with different light curves, and now maybe, and also maybe the complex network can help us to find the differences between light curves, and also the the studying of noises. I think this is a good goal for the KSD study, because by the study of degree of nodes, we are by study of the degree of nodes for a random time series, we are very near to a noise, to a background noise at least, and maybe it can help us to study the noise. But yeah, I have also I have had some studies on transitivity between different types of stars, because it can be influenced by the shape of the light curve, and I can have different values of different range of transitivities for different types, but it still needs to be worked on. Yeah, these are the things I'm thinking about. Yeah.
I was thinking about slide 22. I think you introduced some quantity I was not sure about, but I don't remember the name, so I think it's around 22.
22.
Yeah, transitivity. Can you remind me what is transitivity and what is the meaning?
Yeah. Here we have at least a mathematical equation for that. Transitivity means the number of complete triangle, the fraction of complete triangle to the not completed triangle. The not completed triangles means the triples that need one other edge to be a triangle to be completed. And here we have 3 because as I remember, because every triangle has three nodes, 3 corners, and we consider for 3 nodes. So it should be 3 times for 3 nodes. Okay, and here it is we know, but I'm not sure now about the exact relation between the transitivity but average clustering, but I have done some calculations. Maybe I can find them here. But there is some similarities between them, but they are not the same. And we wanted to study them together to see what's the differences between the hats and lads. And yeah.
Yeah, but I was wondering, but by itself, well, this is a comparison between the average clustering coefficient and transitivity that may rise to some difference between LADs and HATs, as you have just said. But I was wondering, by itself, transitivity, apart from its definition, which is a specific one in networking and so on, what kind of information can give transitivity by itself?
Transitivity, like similar to clustering, speaks about being more connected part of a graph. I think when the clustering is higher, it means in this part of graph, nodes have the tendency to be connected to each other, and I think transitivity has these meaning, or at least follows this concept. I can show you. If there is a study on transitivity in one paper, I just read it. It was interesting for me. It could be used also for noise study. When the noise in a light curve is higher, the transitivity is affected by noise, and the values are closer, are smaller. Sorry, are smaller. And yeah, just transitivity could be used in my next studies, but by now I don't know. Could I answer your question, or?
Yeah, more or less. Thank you.
You're welcome.
Maybe we have to with the non-linear behavior. The big difference between a high amplitude Delta Scuti and a low amplitude is is basically something we don't know at all. It's the non-linear developing of the equation. And it depends of key parameter we don't know actually. And many of these point to this non-linearity. If you read the paper by Maria, you realize that this can be developed in several parts, so indicating that the speed may indicate this developing non-linearity for vision in the world.
Okay. Thank you, Anna. I had a question about, so maybe you don't need the plot, but if you go back where you define the HVG, you have you essentially define, here, an edge as a line of sight between two peaks that stick out. You don't use converting the light curve into this plot here, you lose every time information. Actually, like the frequencies get lost in the process. And for instance, between your peak number 1 and 6, there's a line of sight, and there are 5 or 6 beats of this pulsation thing. Is there any point in trying to use the length of the edges to some analysis? Will you see a difference between three extrema of your light curve connected by 3 lines of sight? So that would be 3 nodes connected with 3 edges. Depending on the time you have between those extrema, that is the length of the edge, if that exists. I'm not sure. Like, would there be any useful information in this? Have you considered that?
Yeah, you're right, but just I consider a time series as a story of star along the time. So for me, it makes sense to consider a non-directed graph or network for a time series, but also we are considering the directed graphs to see what happened when we move against the time, and also just I'm making some results.
But in this case, you're looking at the direction or the order of the sequence of events. Essentially,
Sorry?
you have you resume your light curve in a list of interesting points in time, and this list you lose the actual time that passes between those events.
Okay, this is TESS light curves, and the points are evenly chosen, at least.
No, but look here, for instance. The line of sight you have between peak 1 and 6, or between peak 6 and 8.
This is not a real shape for this light curve. This is just something.
It's an example. I understand your point.
Let's stick with your example here. Between 1 and 6, or between 6 and 8, you have the same kind of edge. This double arrow that goes from one to the other. 1, 6, and 6 to 8. But one is significantly shorter than the other because the time elapsed between those two events. I mean, you have other things happening in the middle, etc. Does the length of that arrow contain any physically relevant information or not? That's my question, essentially. If you don't know, it's okay.
Do you mind if I talk?
Yeah, of course.
Because during your talk, I was inspired. In this moment, I was taking notes because it's true that as far as we know in the last literature, there are no technique in order to conserve But because it's true that whenever you do the passage from a time series to complex network, in this way, in the horizontal visibility gap or in the other technique, in the visibility gap, you are losing information. Indeed, is a mathematical problem that I was thinking about a few weeks ago. There is a way to move from network to time series. No, if you don't consider the distance between the time distance between the nodes, there is no way to. I mean, you can transform the time series to a network, but it's not be active. You cannot pass to the network to the same from the network to the same time time series. But if you can show the slide of the kind of there is a weighted network. You know,
Oh,
that there
yeah,
is,
yeah.
I think that there is a way, but in this case we will be the first one to exploit this technique to weight the link with the distance, with the time distance. So in this case, you conserve the information on the distance between the nodes, and maybe it's possible to move another time from network to the original time series. Or at least you have an information more to do network statistics and so on. So I think it's for me it's an excellent idea that we have to exploit.
Yeah. Yeah. I should think about it more. Thank you. Yeah.
More questions? Well, okay. I'm coming from completely directly another field of research.
Yeah.
Rotation of asteroids. And you say in the last slide that you use Gaia data. So
Yeah.
we are trying to use Gaia data to fit rotation of asteroids. So it's imagine like a potato that is rotating, and we want to see the difference on size and for applying this method, do you need a really complete light curve, or what happens if you have only a few points on the light curve? For example, in the next slide, this one. What happens if you have only 1 point every, I don't know, every cycle? Can you use this method?
Okay, for our star, if the light curve cannot be described completely, so the viewpoints cannot show us the light curve, the real light curve, the complete light curve. Okay. So it's the kind of related to Nyquist frequency of points or so. And about the complex network, we need enough points to making the complex network, and for network parameters to be stable.
Okay.
And I examined that for transitivity and average clustering, and I saw for my light curves, I need at least 2,000 points to have a stable parameters that are not dependent to the size of
okay, so
network.
You need an absolute number, 2,000, but
Yeah.
doesn't care about the the separation on time, for example. If I have 3,000 point, maybe in some part of the curve very dense plotting, and then 1 point, 1 point, 1 time. I have 3,000. Okay, but can be applied with this kind of curve?
I think so. If you
Okay,
have
right.
I think if you have information, you have all your information in this pattern of nodes, you can try.
Okay.
And also maybe some weighted networks.
Okay.
Yeah, maybe.
That's right.
But your data is occultation?
No. It's rotation. It's exactly this magnitude over time.
Okay, because it's the differential the differential albedo from
no, it's area reflecting area of the that potato.
Okay. And you have many gaps, you said, no?
Yeah.
I'm a bit confused because if I properly understand the last question, if you have holes in your lighter, then is for your technique is the same as if you have this hole in one part of the lighter or the hole in another part of the lighter.
You are telling about the size of
No,
network?
I mean, which are the differences between different places where you can have a hole in your lighter.
The different part of a light curve.
Yeah, how it affects to your gap. Yeah.
A gap.
If you have a gap
Yeah.
in one, I don't know, you have like 20 days. You have a big gap in day
Yeah.
19, or you have the same lighter, but your gap is bigger or shorter or whatever in another place. Which are the difference in your result?
Yeah. We avoided gaps in our studies, in our results, and also we excluded the very early and very end of nodes because we want to model a continuous, light curve for the network. And because the very early and very end nodes have some differences. And yeah, we avoided gaps, but it is very good way to do gap filling and have larger networks and graphs and time series with gap that are filled.
That's why I was confused. It is you cannot solve this problem, I think, yet.
I mean, sorry.
Yeah.
I think that is the same problem you have when you move from time domain to frequency domain.
Okay.
I mean, the problem is that
Infinity.
no, okay, no. The problem is that which you have gaps, okay?
Yeah.
So which is the best way to overcome the gaps and to filter out the noise? It's better with classic direct classic discrete Fourier transform and filtering, or maybe obviously we have gaps also in this case, but maybe in I don't know, I don't know the answer, but maybe if we have gaps, the statistics of the networks is sufficiently robust in order to overcome the gaps and filter out the noise.
Yeah, it was just for the first answer. I was thinking that the gaps are not a problem, but they still may become a problem.
Okay.
No, with your previous answer, I understood.
I think that maybe the in a practical way, once one has to make tests with very simple signal. You have a sinus signal.
Yeah.
You put some gaps. You calculate the network. You calculate your statistic. You compare with the whole signal. If it's sufficiently robust, it's good. This is the
and also by just visual imagination. I think gaps will result in some problems. Because of that, I avoid them. You imagine the last point before gap and the first point after gap. So they are like the a first and end point of a light curve, and they can disturb the complex network. So we avoided gaps, but it's good to have more data and more points.
Let's suppose that let's suppose that in this example, in the right example, you quit out the time points 7, 8, 9, 10, 11. Okay, so you have a gap.
Yeah.
Okay, so the only points that are affected in the network are the points 6 and 12. Okay, so you have two clusters with let's suppose that the signal is a sinus. You have two clusters in which the statistics is very robust and is very fitted to sinus wave, and then they are connected by a line. So I think that when you make statistic on this network, you are overcoming the gap.
But why you assume that when you remove this 7, 8, 9, and 10, 11 point, the solution is the same as
Because,
before?
Like, so let's suppose that you quit out on this one.
And you can use
Okay.
where is the pointer.
No, don't worry. So you have this network with a sinus wave, this network with a sinus wave, and this link. Okay? So in the network representation, you have a network with the statistical probability of a sinus wave, a network with a statistical probability of a sinus wave, and a link. Okay? So all that you can measure from the statistical point of view in the nodes affects just a link. I don't know how to say I think, for example, I think that the distribution of nodes are not affected. It's not very affected by.
If I may, you are assuming that the duty cycle is very good. You are only losing like 2 points or 4 points or so on, but there are other cases that you can have a lower duty cycle than 60%, and this is a very big fall. And this is the case that more or less maybe are you talking about. So.
And also, if we have lots of data, we have a repeated cycle. You know, we have a repeated pattern. If we lose some points, we will have still other points to show these things from the light curve. And
Okay, last question. We need to close this up.
To be more clear in the case of gas, when you have gas, you have a window defining it. And by theory, the convolution of the product on the window with the function give the convolution, and you can perform any the transform which indicating what is the window transform. And then you put both, and you see that all theoretical development, including Fourier transform, include the window transform as being in the 70s down 30. So here is the same. I mean, if you have got this includes that your function it has been multiplied by the convolution of the window. So this can help to define some theoretical development.
Okay, I think the discussion can go on offline.
Yes.
Thank you very much again for
Yeah.
this talk, Alan.
I can say so.
yeah.
When you compute your network, it is
Esatto, che si puede comprobar.
that goes from the first point to sequentially from the first point to the